Conservative and non-conservative forces. Objective: to differentiate between conservative and non-conservative forces. We know that work done by a force is equal to the dot product of force and displacement. Let us look at the work done by two different types of forces, gravitation and friction. Consider an object taken from point A to point B along the curve y of x near the Earth's surface. Let us calculate the work done by gravity when object moves through an infinitesimally small distance dr from a point P on the curve. dr is the summation of its displacement along the x-axis dx and its displacement along the y-axis dy. Gravity acts along the y-axis, so work done by gravity dwg is minus mg dy. The total work done by gravity from A to B is integral of minus mg dy from y1 to y2, which is equal to mg into bracket y1 minus y2 bracket closed. Observe that work done by gravity depends on the initial height y1 and the final height y2, and that it does not depend on the shape of path taken by the object between those points. So, it can be said that irrespective of the path between points A and B, work done by gravity is the same. If the object is brought back to A through another path, as the initial and final positions remain the same, the total work done is zero. Such forces whose net work done in a roundabout motion is zero are called conservative forces. Work done by a conservative force is independent of the path taken. It depends on the initial and final position only. Gravitational force, spring force, and electric forces are examples of conservative force. Now, let us look at work done by friction in a roundabout motion. Consider an object of mass m that is moved very slowly through a distance d between points A and B in a straight line on a rough floor with coefficient of friction mu. The frictional force that exists between the surfaces is therefore mu mg. Friction, as you know, acts opposite to the direction of motion. Hence work done by it is minus mu mgd. Now consider another situation where the object is brought from A to B very slowly along a circular path of radius r. Frictional force along the circular curve is mu mg, and it is opposite to the motion of the object at every point. Hence, work done by friction in this case is minus mu mg pi r. Though the initial and final points are the same in both cases, work done by friction is different. So, work done by friction depends on the path taken by the object between initial and final points. Irrespective of the path taken to bring back the object to point A, total work done in the roundabout motion is not zero, as friction acts on the object throughout the path in a direction opposite to that of its motion. Such forces whose work done is not zero in a roundabout motion are called non-conservative forces. When non-conservative forces are at play, energy escapes the system, mostly in the form of heat.
Collisions. Introduction. In the previous topics, we have defined the most important quality which explain about the capability of body to import its motion with another body, which is linear momentum. In this topic, we are going to discuss about the interaction between the two bodies. In general, we say a collision occurred when objects crash to each other. For example, the collision between two automobiles, collision between hammer and nail.
In fact, collisions range from the microscopic scale of subatomic particles to the macroscopic scale of colliding galaxies and stars. The mutual interacting of the particles of bodies for a small interval of time, due to which redistribution of total momentum takes place among themselves, is called collision.
In Rutherford's alpha scattering experiment, alpha particles bombarded with a gold nucleus reveal the inner secrets of an atom. The positive electric field of the gold nucleus abruptly changed the path of an alpha particles so that the interaction process can be called a collision. Collision between two bodies may be in one dimension or two dimensions or even in three dimensions. Objectives: to understand the definition of collision, to know the knowledge of types of collisions. Definition: the mutual interacting of the particles or bodies for a small interval of time, due to which redistribution of total momentum takes place among themselves, is called collision. During collisions, there will be an exchange of momentum between the bodies. However, the kinetic energy of the bodies may remain constant or change. Accordingly, the collisions are classified into two kinds. They are: 1. Elastic collisions. 2. Inelastic collisions. Elastic collisions: the collisions in which both momentum and kinetic energy remain constant or unchanged are known as elastic collisions. Let us see the examples of elastic collisions. Examples of elastic collisions: 1. The collisions between atomic and subatomic particles, atomic nuclei, fundamental particles, etc. Inelastic collisions: the collisions in which only momentum of the system is conserved but kinetic energy is not conserved is called inelastic collision. Let us see the examples of elastic collisions. Examples of inelastic collisions: 1. Collision between cricket bat and ball. 2. Collision between two cars. Perfectly inelastic collision: when two bodies stick together after collision, the collision is said to be perfectly inelastic collision. In inelastic collisions, kinetic energy is not conserved. Example: the collisions between bullet and its target, when the bullet remains embedded in the target, is an example of perfectly inelastic collision. During these collisions, the loss of kinetic energy appear in the form of heat or as excitation energy, as in the case of atomic collisions. Perfectly inelastic collision: let us consider a perfectly inelastic collision. That is, two particles of masses m1 and m2 have velocities u1 and u2 respectively before collision. After collision, they stick together and move with a common velocity v1. Then, according to the law of conservation of linear momentum, therefore, m1 u1 plus m2 u2 is equal to m1 plus m2 of v. Therefore, v is equal to m1 u1 plus m2 u2 by m1 plus m2. If the values of u1 and u2 are known, the final common velocity can be determined.